My presentation is going to be the last one for this hall. The title is Building a Smart Recommender System Across Line Services, and the presenter is myself, Namikawa. Let me introduce myself. I am a fellow of Line. When you hear fellow, you may think that's whether it is an executive or engineer, rather mysterious title, but being a fellow is to create a machine learning system, looking over the line-wide various services. So today, I'm going to talk about the system which provide consistent recommendation for various types of line services. We created this, so let me share that with you. And before I go into the detail, let me talk about the context of the development. We have diverse and wide types of services in lines, stickers, news, manga. Some of the services have tremendous amount of content. In those cases, the user cannot really look for the one that they really want to consume. Therefore, we need to have recommendation system so that users can simply find the information that they need. So that's why LINE provides services based on the recommendation services. Against that backdrop, even though users go to those pages of services, the myriads of services available in one line, so that just checking out each of them will be time consuming. So when a new service is added to the one which user may find it useful, it is rather difficult. And also, fresh information may lose its value when time passes. Therefore, just giving the recommendation is not sufficient. So, even inside the service, you need to provide information about the contents, which means that we have to combine services plus contents. I think you have already heard about this many times today, but at the top of the screen you can find contents, the red area. I think some of you have noticed the contents on top. And at the beginning, we had just weather and those information. But now you can see manga, fortune telling, stickers, and then news. In case of stickers, sticker shop, and news contents are held by news. Line news manga is in line manga. So contents are coming from different type of services. So you need to select one service from the content. So how do we do that? So this is a conceptual view of the selecting the contents for the services. So first, collect contents from different services and select. You can find the brain-like picture in the middle, but this is a central system which select the recommendation or combine the services which this particular user probably prefer to have, so that optimization logic is important. It is possible to put the necessary information on the line screen, but to have the most preferable information for the user, probably we have to have some kind of a centralized system to aggregate the information. This central system is the service-wide contents recommendation system, which I would like to give you the details soon. So before I talk about the recommendation system, let's take a stock of history of Smart Channel based on the graph. This is the history of Smart Channel and the number of impressions from the beginning of the services. And the blue is the number of impressions for the users per day. And the green is the score. These are the ratio between the click and also the stoppage of the services. So click itself is good, it's positive because they wanted to look at it. But if you select stop that service, means that they were not interested in that information. So higher the ratio, the users liked that content. So that higher the better. So let's look at this area. The green area increased. And this period, what did we do to increase the green line? Even for the blue lines, we increased the types of contents to increase the numbers, and also we had to link our services among ourselves. So some interesting stories there. But today I'd like to concentrate on the green line, how to increase the satisfaction level of the users in scores. So, as for the smart channel development and planning, will be given by the speakers on the screens. So please go and listen to them if you are interested in. All right, then let's talk about the architecture of this recommendation system. So I'm going to talk about the machine learning system. Whether it is ML or any other system, you have to have certain limitation and requirement at the beginning of the design. So we looked at these parameters at the beginnings. So when you think of it, there are three conditions that we have to meet. First one is the cooperation with existing recommendation system. Second one, scalability, which always become a problem for line. And the third one is the people who are not familiar with the system don't know much about this, but this is the problem called cold start problem. So for each of them, I would like to give you what happened. As I stated at the beginnings, we already have a recommendation system in many of the line services. These services are just a part of them, and the recommendation system already exists, and the contents are shown accordingly. And if you look at the chart, and this is part of the example in the news, this red area gives the articles probably preferred by the users. As for the sticker shops, they also give the stickers probably preferred by the users. So for these different services, the different type of recommendation services are moving.
There are several reasons. Maybe some are in case where the implementations are different, or some cases they use different algorithm. Maybe it's a collaborative filtering, or maybe it's using this degree of similarities of the images and text, and also users' behavior log and also image analytics are combined with deep learning. So there are different approaches. There are different purposes. For some services, they are trying to improve CTR. The other services are trying to improve the revenue. So the purposes are different. So what we were thinking at the beginning is we have this different recommendation assets. We have to ignore everything and start from scratch, or should we use whatever is available to us and reuse them? That's the first condition which we have to think about. The next one is a scalability. So itself, as you see the numbers, this is the most recent numbers on the smart channels. Impression is we have about 500 million impressions per day, and also 100 million users, and also we have 60,000 new contents to be added per day. Well, we were already predicting this scale from the start. So in order to go across the different services, we have to think about this scale. to handle the data. That was the second condition. And the third, this is quite provocative statement, but the contents which have to be displayed, the newer the better. So smart channels, the very top part of the chat tab is smart channel. This is really important location, and I think maybe the contents which lose value over time are always available, so should not be displayed because this is really important location. We don't have to display that information at really important location. So that's why the newer content should be displayed at that important locations at the chat tab top. But when we are trying to recommend the newer content, it's a little bit difficult. And that is what we call as cold start issue. So what this means is machine learning, yes, we have more data, we have better machine learning. But when it comes to the new content, no one has really seen that content. So important data source, which is a user behavior log or user patterns, are not collected yet. So when we think about this recommendation system, we have to really be good at displaying the newer content. So even though we do not have enough user behaviors or user behavior patterns log, we still need to be able to recommend the better content. So those are the three conditions which we had to consider. Based upon that, what we decided to develop is described on this slide. So let me first give you the overall configuration of the system. As you see far left, this is a recommender system of each service. So we decided to reuse the recommender system of each service. What system is going to behave is from each service, we have a k number of the top items to be cast on the central location. And after that, from the application, we have a request. So since it will be displayed onto the tab. If we have the request, then we have the system called ranker. This receives the requests from the user. So first, we have to set the user ID, and from the cache, we are going to get the item list. This item list is going to be displayable, and this is generated by the recommendation system of each service. The ranker system, for that specific user, they are going to choose one content which is most suitable to this user at that moment. Well, since it's a machine learning, so it has to learn. So we need to really create the system for the learning purpose. And what this is doing is once content is displayed, maybe impression or maybe clicking or clicking the cross mark, that will be incorporated into the service, and then it will be incorporated into the trainer system. So this trainer model or trainer system is computing the machine learning, and then the parameters are going to be synchronized with the ranker. Ranker always incorporates so that it will always update the model to the latest. So that's the system. So this is the entire architecture. So let me go each one. First, I'd like to talk about the ranker, choosing the contents. So every time ranker receives the request, ranker is going to put the prediction score for each item list, meaning how likely the user would like to receive this content. Of course, it depends on the user, and also, of course, the user preference is different. So that's why the prediction score is computed every request. Ranker is going to pick the highest number of the score. This computation, in terms of the algorithm, is a contextual bandits. That's the algorithm which is being used. So when I talk about the system requirements, the constraint requirements, this is trying to find the newer content. So yes, we assume that maybe we may not have enough data for certain content. So maybe sometimes the predicted score may not be correct. But we have to still display the contents to the users. Otherwise, we cannot get the data. So getting or acquiring the data, trying to improve the accuracy, and also at the same time, we have to select the best item. This is exploration and exploitation. So we have to have a best balance between exploration and exploitation and trying to have the best contents. That's what we call as bandit algorithm. And especially we are using the contextual bandit algorithm in this case. So now let me talk about the specific models used in bandit algorithm. Currently, we are using Bayesian factorization machine. So first, let me talk about the factorization machine. So factorization machine is using the feature value interaction, which is inputted. So let's say feature value, age and gender are coming in as feature value, then maybe we are able to describe the and condition of age and gender. So in order to allow this factorization machine in bandit algorithm, we have Bayesian factorization machine. Even though we have the models, we have to have the feature value. So let me talk about the feature value. There are three types. Number one is going from the left, user and item embedded vector dot product. So what this means is for each user multiplied by item, we create that information and trying to compute the feature value. So for some user, do they like the contents or not? So this can be computed with really thorough personalization. The other is a user feature. So this is the predicted age or gender. That's the attributes coming in. The third is others. Let's say maybe the current time. Maybe in every hour, it can be encoded. So what about the model output? Impression is 0.5, click is 1.0, and mute is 0.0. So if it's clicked, it's positive. If they chose not to display, it's negative. And if it's not, if it's impression, it's neutral. So that's how the system is going through the online learning algorithm. So now, what kind of system is used to learn these parameters? So this is the training side system architecture. As you see, the main character is a parameter server, which is in orange. So this is a protagonist of this system. What this parameter server is doing, the first one is a trainer, which is at the top left. So the line service has huge volume of traffic. So we have to parallelize the machine learning. That's the scale which we have to face. So of course we use several nodes and several processors trying to go through the learning of the model. If we have the discrete learning, then that is going to be discreted. That does not leverage the benefit of parallelization. So we have to aggregate those learning outcomes at certain location. That's how we leverage a huge volume data to learn. So that's why we need to have that system. So each trainer is going through the learning, and that parameter server is going to receive the updates of the parameters, and then parameter server is going to reflect those updates and return to the trainer. And also the system is going to be asked for the parameters. Obtained parameters are used for calculating the ranking.
で、先ほどパラメータサーバーの話をしたんですけれども、
I talked about the parameter server, but let me go into the deeper into the subject and talk about the parallelization. I'm going to give you some mathematical equation, but it's not going to be that detailed, so please listen to it casually. Please look at this left-hand side table. 3 lines are there, horizontal lines. Middle is the parameter server. The top and the bottom, trainer A and B. So there are 2 trainers. So this is one example. So what is the situation here? First, trainer A receives the parameter from the parameter server, learn for a little bit, and when learning advances, then the difference goes to parameter server, and again it receives another parameter. While it is doing that, trainer B communicate with parameter server for several times. Why is that? Because trainer B has faster computational power, or it receives more logs for the parameters. So the progress velocity of the learnings different. So in this situation, asynchronous distributed learning. But usually synchronous and also asynchronous, there are 2 types of learnings. But in case of synchronous works well, then it is usually better to use the synchronous online learnings and recommended for the machine learnings. But this is the online learning. We wanted to reduce the maintenance power, so that we should really know that the what's reaching to that. But this algorithm, bandit algorithm, cannot really anticipate how much data is going to be given to you, so that asynchronous online learning is necessary. And in case of that, the parameter A can learn it, but parameter B makes so much progress in the learnings, so that the data sent to the trainer B is already obsolete. So what do we do? One way is to discard all the data, but that's wasteful, so that even the old data should be also utilized for this. So in this case, we prepared this mathematical equation. There are 2 types of terms. First one is green circle. This is the deceleration parameters. Parameter servers, which they have right now, and the past parameter the trainer received, the bigger the difference, they decelerate, so that the difference between the 2 should be smaller. So the difference is already old. So when you apply that as it is, then the direction of the learning may be different from the original direction, and it may also break that learnings. So that's why they said the deceleration. Second one is about the backtrack, which is indicated by blue lines. So just make that parameter into the older one just a little bit. So the situation when the trainer A learned was old, and whether you can apply that or not, and the closer it goes to the time point when they learn, it is better. But you can't really go back to that point exactly, but just go a little bit, go back to that point so that keeping learning contents always relevant to that original target. So with combining these two terms, asynchronous learning can also use the data, which won't be so wasteful. So you can learn this, but deceleration, backstoppings also make the learning velocity a little bit slower. So we don't really want to do it unless it breaks. So we have to use engineering methodology by creating the load balancer. So the same model have to go to the same process. By doing so, we don't have to have the so much difference in the quantity of the data, and try not to have the parallelization. And in principle, we don't want to have a parallelization so much so that there will be a great difference between the two. If there are some too much difference, then we apply this asynchronous learnings. So that was the way that we used for this. So this is going to be the last slide for the ML. So how to use the parameters of the ML architecture. The model parameters were divided into three: Bayesian factorization, and the second one is item embedding. The third one is user embeddings. Bayesian factorization machine and item embeddings are going through parameter servers and stored in Redis. Meanwhile, user embeddings go straight to storage without going through the parameter server. Because we have more than 100 million users for line services, so that if we go through user embeddings, the size is going to be tremendous. So it is very difficult to have cache. Bayesian model, item embeddings. The calculation can be done in several nodes, but user embeddings that the several nodes do not calculate at the same time. If should that happens, the probability is very low, so that statistically you can ignore that type of incidence. So that the when you think of the accuracy of the learnings and also the overall dependency of this situation, we decided to do this. So up to now, we talked about the machine learning. I'm sure that you're already tired listening to this very complex contents. So let me talk about the A/B test. So we have ML architecture, and the model should be always tuned, and you need to have analytics and then test. So that's why we also use analytics and also test to tune the overall mechanics. So before or at the beginning, I would like to talk about which index we decided to use. When you improve model by tuning it, what is the definition of being better? So mathematically, we have to define being better. So as I stated at the beginning, we are using CTR and also XCTR. the score, we call it. And there are three reasons that we decided to use this. First one is that we conducted the survey for users, which contents you like. And comparing that surveys and scores, then there were very strong correlation between the two, much better than a CTR. And we decided that the survey is really reflected in that indicators. And also calculation is simple. Third one is chronologically stable and easy to handle. So this chronological stability is probably you need to have some explanation. So let's use this. This is the graph. Blue shows the score, and the red is CTR, and the green is X CTR. So which means that the user closed that service. So red line, green line has some peaks, and the peaks and deceleration. But when it peak, what happens? It's usually new contents are released, or these services are shown to the new users. So if you understand it in natural languages, the user find it so new, so they just click it, and sometimes they mute it. But when they get accustomed to seeing it, then they don't react. That's how I understand. It has nothing to do with user satisfaction level, whether it is novel thing for them or not. So that it's really not something to do with satisfaction level. So if we set the CTR as the main evaluators, then we are going to release the very strange or very different type of content, so that user always think it's new. But these numbers can also related to the score. Then a score is easy to handle because it does not really decelerate along with the chronological line. So now, when we decide to use these numbers as the main scores, then we have to look at them on the dashboard. So that's why we created this, and the day-to-day, always look at them. Furthermore, the contents are shown in the various services, and sometimes you cannot detect the anomaly by just looking at the dashboard. So we have to have a system to detect anomaly, and you have to send an alert of anomaly. And we send alert to Slacks, and we try to react to it. So this is the offline test. There are offline test and the A/B test, which actually shown to the users, and then we are repeating this so many times. To do the A/B test, you have to develop a system. The offline test is cheaper because we don't really have to develop the environment. To do the offline test, we need to accumulate the log in a Hadoop cluster and try to write that environment with Jupyter, and we deploy the environment which is closer or almost similar to the real live situation, and then try to evaluate it. And the algorithm is a Pandit algorithm, so that we use the algorithm day to day. So the last one is A/B test.
So Livra, which is the system for A/B test, and this is their dashboard. So far left is a service list, and there are different services using Livra to do the A/B testing. For smart channels, we are also using this A/B test to see and choose the good models for improvement. So far, I have been talking about the architecture and data analytics and also A/B test environment. So lastly, I'd like to show you some case studies of our A/B test. For smart channels, the recommendation improvements itself required several A/B tests, and I'd like to show you some 3 examples which show some great cases. Switching to the models. So I think I talked about the models at the ML architecture. So I talked about the Bayesian factorization machine. At the beginning, we were using different models. It was Lean UCB, and this is also one of the contextual bandits. It's linear model. So linear model, what does this mean? I think there are different meanings, but this is really important. It's really easy to do the parallel computing. So since it's linear, so the delta can be added to have exactly the same. So I think we don't really have to go through the algorithm for the parallelization. It's easy to deploy. So we were using this at the beginning. However, I think maybe for the accuracy, we should use factorization machine. CTR improved, and then cross CTR is negative. Yes, negative is better because they don't like the contents, and the score improves. And maybe their parallelism computation was required, so it was a little bit costly, but I think it was worth it. Next is the recommendation system, which I have been talking about. And the next is the UI, not the logic. So UI improvement was the next contributor. In the smart channel, there were no image displayed on the smart channel. We were only showing the text. But now we started to show some image, and then we did the A/B test. Well, the image is quite small, so I was not really sure if that was effective or not with that size. Well, maybe sometimes we do not have the available image which can best fit to this size, so we had additional development, so it was a bit expensive. Does this really work? And we tried to see how it's effective in A/B test, and it was really great, great success because the CTR improved 56% and the CTR plus 35%. So maybe the model doesn't really matter. And also the cross CTR also increased. That was not good. So maybe positive and negative to balance. I think the score itself improves. So maybe by showing the image, users can choose what they may like. So overall, this is showing some positive outcome. And also personally, it was really difficult for me to accept that. Just changing UI also was a big contributor. The third one is the model. We are adding embedding. There was no such thing. And without this, we were not able to do the personalization. So of course, we should have used embedding. But each service recommendation system is already personalized. So maybe without having that, we already have the recommendation system which is personalized, so it's not a must. So under those circumstances, when we have the feature value, what is going to happen? And to see that, we did A/B test. So as you see the numbers, maybe a little bit less impactful. CTR improved, and also the cross CTR decreased, and the score, rather than adding the image, I think a score even improves more. So maybe this is showing the better results than changing UI. Well, there's no negative impact. So this was showing quite a positive outcome. So this is how we conduct A/B tests, trying to change the model, trying to adapt the UI. What would we want to go? Where would we want to go? That's something which I'd like to touch upon at the very end. So I think I showed this slide. Currently, each service sends the recommendation results, and then we choose amongst them. So it's sort of a one way. But to really have the extreme optimization, I think the system in the center and also each service have to be coupled so that it should be better optimization. So this type of coupling have to be conducted so that we will be more accurate. But for that purpose, each recommendation system of the different services, if we have different systems, of course it will be expensive. So each service recommender system have to be unified, and that's something which we are working on. And the data infrastructure cluster is now unified, and also machine learning computation system to be clustered so that machine learning can be conducted in the similar environment. So by improving the system, each service recommender system can be unified so that it can be orchestrated to the company-wide system. That's all. Thank you very much for your attention. Thank you.